Okay, yeah. So, welcome everyone. So, we'll try not to take much time today, and hopefully, we have enough time to like just play around with some data structure and algorithm questions. And yeah, we'll start. So, some of the major data structure and algorithm topics we want to like just treat today is the list data structure, queue, stack, and map data structures. So, basically, so like I said, I want us to like just um rush through some of these data algorithms so that we can just play around some questions and just see how this can actually be useful in the real world. So, what is a lead data structure? So, basically, a lead data structure is a data structure that stores an order sequence of elements. So, last class we discussed about array data structure, and you see how you can actually add some items in an array and actually retrieve some of those items from the array. So you see the same thing is applicable here. So because one way an array is a kind of a list data structure, but we'll not go deep into that. But because they have like similar, you have similar experience while working with an array. So elements can be added and removed from the list, and they can be accessed by their position in the list. The same thing with what you experience with an array. So, and these are the operations that can be performed by an array, inserting, appending, and deleting elements from the array. So, yeah, so the major examples of list data structure is the array list and the linked list. So, we started this class majorly using Java, right? So, majorly where you hear data structure like array list in Java, I think C Sharp also, and some other languages. But in JavaScript, so you now get to see array list because in program languages like Java, arrays are fixed length. So I wanted you guys to like maybe get a jotter or anything so that you can just follow me along and understand some of the major thing I'm talking about. So, in languages like JavaScript, arrays are dynamic. You get so meaning like what we mentioned last week. You see that we have to like kind of give it a kind of fixed size so that the system understands or the program understand the number of elements that are expected in that particular array. But array list here is kind of dynamic. It's a bit different from that. So in Java, like I said, I want to kind of clarify that part. In Java, we have arrays. We also have array list. So array list is dynamic, but array is not dynamic, meaning that they have fixed length, basically. So, but in JavaScript, arrays are kind of dynamic. So those of you that have worked with maybe JavaScript, are currently working with JavaScript, you find out that when you are declaring an array, you don't need to like give it a kind of fixed length. That's in JavaScript, but in Java, it's not that's not the case. So the same thing, very similar to the way an array operates, you can access element by their index. So this is not the index, obviously, because indexing here start with zero, and this is just like the number of elements that can you can add more element, but this is just basically a kind of pictorial view of the array list. So we have the linked list also. So what is like a linked list? Let me start and let us discuss more about array list, then we'll talk about linked list later. So array list is a dynamic array implementation that grows or shrink automatically as new elements are added or removed. So now you need to understand when I mean something is dynamic, meaning that when you add new elements into that particular array, they can kind of grow and they can shrink depending on the number of elements that are currently in that particular array. So in Java, array list kind of increase by 50% of the initial array size. So for example, let's say we started with 10. We have 10 let me say by default. So we have like 10 items in an array, and you want to like add, let's say, the 11th item in that particular array list. So what happens is that Java under the hood increase the size of that array list by 50%. So you see what happens. So 50% of 10 is 15. Then it grows that way. Then when you kind of reduce the number of elements in the array, then you find a way to like shrink also. So that's what is talking to grows or shrinks. And some of you will be asking, why are we even discussing about array data structure algorithms? Some of you are programmers and you've been writing code for long, and what you do is when you're kind of working in a particular project, what you do is basically is just use any data structure that you feel like. You just feel, yeah, an array will work, or a linked list will work, or an hash map, a map will work, or any other thing will work. So before you make some of the decision, you need to like understand the time complexity, the space complexity of that particular array, and some of the things that are involved, or understand details about that particular array. So I'll show you some of the little. Okay, I want you to see some things. Can you still see my screen? So basically, I have some snippet of code here to just show you how an array list look like in code. So this is a Java code. So for those that are interested in Java or are already working in Java, I will find way to kind of share this code snippet to you guys. So I have an example here, how you can add an element into the array list, and how you can get element outside or out of the array. So basically, this is a string, an array list of strings. So another thing you should take note also when you're working with languages like Java, C Sharp, or C++, or some of them like that, they are kind of typed. They are strictly typed. I know, yeah, in JavaScript is not typed. Only if you want to use like TypeScript. So when you're declaring an array list, you need to decide or specify the kind of data structure, or the kind of element that will be inside the array, basically the data type of the elements in the array. So here now we declare element. Let's say I change this to integers, for example. You see what happens, and it started complaining that okay, you specify that. Can I take this out? So you specify that you be adding string into this particular array, but integer into this particular array, but you give us string. So I think if you check here, it can give you some of the errors. Yeah, so when you want to retrieve an element out of an array list, so basically what you do is to call the dot get element. This is strictly for Java. So I think it's similar for C Sharp. So you can still do similar operation, perform similar operation in C Sharp also. So yeah, so let's go back to linked list. So I just want to like rush through some of this so that we can just play around them. So I give you an example or more idea about the way array list increase or shrink in size. So you see what happens here, 15 here, when the size increases to like 50, about 15, then you want to add like the 16 or the 17 elements. What happens is that if you take your calculator and divide this by 2, divide 15 by 2, and you find out that it has increased 15% again, same thing down the line, keeps going that way. And let's talk about linked list. So what is linked list? And I've mentioned array list, and I'll give you some ideas about array list. So now let's talk about linked list. Linked list is a structure that consists of sequence of nodes where each node contains a data element that reference the next node. So basically, so imagine, I just want to give you an idea. Imagine what we have in array list, where we have where we have this is an array list, right? So we add this element item, right, Volvo, to this cars array list. So now imagine that this particular one here as a node or another additional object that is kind of that is pointing to where or the location of the next object. So that's kind of in a simple way what that is saying. So each one, so this is an element here, and it has a kind of pointer that points to that reference the next node. So node, just the nodes are like items, like in array list now. So number of um or just see it as items. So now the same thing applicable to the next node, to the next node, to the last one that points to null. So like I said, some of that structure can be very helpful when you are trying to kind of perform some operation, but you might not understand now because you don't even understand, like say, the time complexity or the space complexity of this, and you feel like, why do I need something that can do that? Why do I need something that can do that when I already have an array list? So let me go to the next slide. So now when it comes to the time complexity of when it comes to time complexity, like this graph is kind of showing you, last class we mentioned, we show you we talked about the big O, and I just decided to like add a kind of picture of what the big O actually looks like. So when you write any algorithm, or when there's a particular data structure that have this kind of time complexity, maybe when you're retrieving or when you're adding any item into, or any element into that particular data structure. So you can see here that um, when you have something that can insert into that particular array with in O of one, you see here it says excellent, meaning that it's kind of perfect. Or O of log one is still good by the color. You see that we can identify them by the color here. And that means that, let's say you're working with any data structure, you need to understand how long it takes to add item into that particular data structure, and how long it takes to retrieve elements from that particular data structure. So if you have any question, you can just unmute your mic and ask questions directly. So here you see the ones that are variable here is O of n squared, or O of n 2 raised to power n, like that. So just have this picture in mind, or if possible screenshot. Okay, fine. I'll be sharing this slide so that you can have an idea in the future. So now, what is the time complexity of array list? So when you are accessing an element in an array list, it is O of one, meaning that you have when you are performing this kind of operation, and you say, let's say, get the element in index 0, or index 1, or index 5 million, depending on the size of that particular array. So it is O of 1. So it's very fast to get items. So that means if I'm working on it and I just feel like, fine, I need something that can actually help me get the details of the content of that particular element by index. So it's easy for me to just say, okay, fine, use dot get, or just get it with index, and that's in O of one. So when you're adding or removing element at the end of the list, it is still O of one. O of one. That's when you're adding. Take note, when you're adding or removing an element at the end of the list, it is O of one. I mean, that's kind of faster. It's faster with an array list. So if you have, let's say, a particular program or an algorithm that you need to add something or remove something at the end of the list, so you can say, fine, array list is kind of perfect for you, because removing elements is O of one, meaning, and remember this chart that I just shown here, meaning that it's good. If you have something that removes with O of one, that means it's good. It's fast. I remember we talked about time complexity and space complexity last time, so I feel you can watch that video and understand more about it. So adding or removing an element at a specific index is O of n. So why is this O of n? So when something is O of n, I think one of the things we discussed last week is this n represents the number of items in the array. So basically, what we are saying is n here now is, let's say we have like 10 or 50 items inside this particular array now. N is the number, like when you count it, 1, 2, 3, 4. Yes, so if you are saying here now that what is n, what does n mean? Is the number of items inside a particular array. Or yeah. So now if you're adding to a specific index, so imagine you have let's say an array that has, like, let's say 1 million records, or 2 million records, and it takes, let's assume it takes like 1 second to like I to move between each item. So that's just an assumption. So let's say it takes like 1 second to move through each item. So I want to like kind of have a picture of it. So it means that if you want to update the value in index, let's say 900,000, for example, that means it's going to like go, if you do your calculation, like 1 second times 900,000 and divide it by 60, so that you have how many minutes to take it to, your stem will just be there like waiting. I'm just assuming that it takes 1 second to like iterate or move from one item to another. So imagine that kind of thing. So when you're working with structure and algorithms, or when you're writing your code, you want to use, when you need to like update something in the particular index, you don't want to, it's only if array list is like the only option that you have. So you know that what will happen is going to be all open. It's going to iterate through each one. That means you just be there waiting. That's if you have like large records. So what's the space complexity of array list? So it's still low of n, the same thing where n is the size of the list, and this is because underlying array used to store the elements as ought to store the elements has to be allocated and resized as necessary to accommodate new elements. So you understand what's happening. So when you want to add new element, then you know it keeps increasing, and I think that's kind of still okay. So now what about linked list? So now, we've talked about array list and just add some of those numbers, O of 1, O of 1, then O of n. That's when you're adding or removing in a particular index. So what about linked list? So before we even talk more about linked list, I want to show you what a linked list looks like. So you will notice that the only difference between this, the array list here in Java, and linked list here is just the name. You see that they have similar code. That's because in Java, that's because in Java they actually implement. Let me show you the source code for this, for example. I didn't write this. So if you see here, they actually implement the list interface here. Like they implement the list interface here. This is not. This is just the Java implementation of linked list. So the same thing is happening here. If you go to if you click control then click on this in your ID, it's going to show you the implementation. So you see what they did here. You don't need to really understand this for now. You can explore that later. But you see that it actually implements the list. So it's one way means that you can actually use some of the methods that are available in list. You can also use it here in linked list. You can use it in array list also. So you see that they have the same similar structure, but the difference is that when you're adding items or when you're retrieving item here in linked list and array list, the takes different time, or they have different approach into adding or retrieving elements from your data structure. So it's very similar, like I said, in Java. So another reason why we decide to kind of use Java here is because Java, for example, has some of this already implemented. If, let's say, for example, you need to use a linked list, you now decide, okay, fine, linked list is the most preferred data structure for me in JavaScript, for example, you need to like write your own implementation, or maybe use a library that's already have some of linked list implementation. So that's another thing you need to take note. Java already has some of these things implemented inbuilt. You understand? So, but you know that in maybe some I think Java, like I don't know, definitely there are some libraries that we provide that for you. I think in C Sharp also you have some of these things already implemented inbuilt. So that's why Java is kind of a bit perfect to explain some of these abstraction algorithm. You don't need to stress. You see, we are writing very little to zero code. Okay. No. So what we are trying to do is to just explain data structure and algorithms using Java, because, like I said, it's kind of a bit easier to show you how some of this thing works. You see, everything you see here is kind of still easy for you to like implement the same thing. You don't need to like, maybe when you're studying data structure and algorithm, it's not really about a particular language, but there are some language that it's kind of a bit easy for you to understand what's actually happening. So that's the reason why I'm mentioning JavaScript. I'm giving you the ideas. I talked about arrays in JavaScript and arrays in Java, for example. You get, so in other languages like Python. So you have dictionaries, or I think you have a list also in Python. So this some of this time complexity and space complexity still stands. Those principles still stands. So it's not kind of we are only using Java here, meaning that because definitely I can't show you an implementation in C Sharp. I can't show you. I can't. That would be a waste of our time. Yeah, but understand the way they work. I'm not showing you syntax. I'm not. You see, that I'm not even showing you more of code. I'm talking more. I'm showing you more of their time complexity and space complex and what you need to understand. And this same principle applies when you're working with JavaScript or C Sharp or C++ and the likes. Do you get? So I think that should, did I answer your question? I don't know. I don't know if you guys are. Yeah, yeah. So now let's continue with linked list. So when you want to access an element by its index, you see now when you want to retrieve an element by index using a linked list, now that's O of n because it needs to like iterate through it. So when you're trying to get, let me show you that picture. So let's say, let me just say this again. So when you're trying to access an element by its index, it is O of n. And remember this picture that we have here. Anything O of n means that is fair enough, but it's not excellent, it's not good. Do you get? But it's still okay, we can still manage it. So and that's because when you want to get an element, let's say you want to get an element in let's say this is 0, 1, 2, 3, and you want to get this particular element. So let's go back to the code. Let's say I want to get an element in index 3 here, for example, 0, 1, 2, 3. So for example, so what will happen is that you guys are not, you will not really see the difference because now you're maybe the computer I'm currently using now is a bit fast, and two, we don't really have how many elements we have. We have like 4 elements in this particular linked list. So imagine we have like billions of records. So you're trying to like retrieve when you're trying to like retrieve these elements in the elements in that's with index 3, for example, it takes more time. That means that's like I trade through everything. So it moves from here, down here, like that. So if you check the implementation, I'm not going to waste much time on that, but let me just show you the implementation. You see that over here we have let me show you the node. Over here you see that uh, each node here has a next and a previous, then the detail of that particular the current item. So what you see here, don't get confused about the syntax. What you see here is just saying each node, each element has a pointer to the next one and to the previous one. Do you get? So you guys understand that. So each element, this node is an item in the array in the linked list. Each one is has a pointer to the previous and the next one. So you don't need to understand this in depth. You can read about the implementation of a linked list and you kind of have more understanding to what I'm saying. So each element, like I said, has a pointer to the next and the previous one. So and like I was explaining using this image, you said that before you can, that meaning that if you need to like access this U, like you save you, it will move from here down like this down till it gets here. But when it comes to array list, it doesn't care, it just goes to that particular index. So imagine you need to like go through all these routes to get to this, or you can just go there directly. So which one is faster? Meaning that the one with all of one, that's a array list, is kind of faster than a linked list. That's when you're trying to retrieve item in a particular index. So now, when you want to add or remove elements at the beginning or the end of the list, it is O of 1. So when you want to add or remove an element at the beginning or the end of the list, it is O of 1. So if you remember for array list here, when you want to add, let's say when you want to add or remove elements at the end, just at the end, it is O of 1. The same thing here, when you want to add, but that one is just talking to the end, right? The end. If you want to add element to the beginning, then that's a longer process. So when you want to add or remove elements at the beginning or at the end of the linked list, is O of 1, meaning it's faster. Remember when we talked about the big O? So O of 1 is kind of faster. So you need to understand that. So if you are kind of choosing between array list or linked list, definitely you will think about, okay, am I going to be adding more items at the beginning or at the end of this particular um, um, data? So you definitely want to like think about, okay, am I going to be going for a linked list or an array list? So you need to think about it. So when you want to add or remove an element at a specific index, it is O of 1, O of n. So because it has to traverse through it and replace that particular item. So that's O of n. I think it's a bit similar to this. When you want to add or remove element at a specific index, it's O of 1. The only difference is this you can add to the beginning or the end and it's still O of 1. So the same thing, the time and space complexity is O of n, similar to that of array list. So now let's look at the performance of both when you're adding element. So here, if you see this chart here, so it's talking about this, the x-axis here is time, and the y-axis here is the operation. So let's say you want to add an element into your array list. See what happens. It takes more time, like by this drive, it takes more time, like it's a bit longer than this, than when you want to add an item into a linked list. So that's because, let's say, I showed you a structure the other time, a kind of chart the other time, that when you're trying to like add new items, let's say you have the initial value is 10 and you want to add like two or three more other elements, what happens is that it's going to create a new array, then find a way to like kind of increase it. That's happening under the hood. It's going to look for a way to like increase the size of the array and move everything, copy everything from that old one to the new one. Do you get? So imagine how long it will take. Let's say you have like 1 million, and let's say you want to add let's say your 1 million and one something item. So that means it's going to create a new array, increase the size of that array list by 50%, and copy everything down to the new one. So now for a linked list, it's a bit faster when you want to add an item into the array. So when you want to retrieve from an array list, you see it's faster because it's faster than a linked list. And can someone tell me why it's faster? I want to ask question. So why do you think it's faster to remove to get an item from an array list than a linked list? Let me see. Is anybody? So you can drop that in the chat. So why do you think it is faster to, I mentioned it the other time, like, why do you think it's faster to remove? Yeah, you can unmute. You can unmute yourself and speak. I think someone raised their hands. I said, why do you think it's faster to retrieve elements in array list than a linked list? Why do you think it's faster? You guys should think. Why? So that means nobody has me understand or nobody has followed me and you guys didn't ask question. Is that the case? Okay, so unmute yourself. Okay, try. It's faster to retrieve. Yeah, yeah. So that's the thing. You're actually right. So imagine you're in an interview and they ask you that kind of question. So they can ask you a question like that, which is faster to retrieve an item from the array list, and you've passed it because, and you gave a reason, because an array list doesn't really need to like iterate to traverse through each element in the list to get to any when you provide the index. So, but in a linked list, it needs to like the details, like they are all kind of linked from this picture. So to get to this, you need to move from here. You need to get details here. Check, is it the one? You move to the next one. Get details of the next one. Is it the one? Then till you get the particular one. So that means you need to like iterate through everything. But in case of an array list, you don't need to do that. You just need to like just go to the computer will not actually do it. You just go to that particular index and you have all the details. So so now let's go. Let's continue. So when you are okay, okay, Okay. Yeah, so I intend to like show that in code. So in that case, let's say you don't know the index. You know, the scenario I gave is when you want to retrieve, you want to get an item and you know the index, right? In the case of array list is faster, it's all of one. But when you don't know the index, the worst case scenario will be when that particular item is in the last is at the list. So imagine you know the index, right? If you know the index and it's theory, you just go is and for array list, you just use get, go to this particular index and retrieve that value for you. But in a case whereby you are not sure, you want to like confirm, you want to like check if that particular value is inside that array, you want to like retrieve it by the value. Let's say you know the value is let's say two. You need to like iterate through everything. So you it's going to be O of one only if that particular index is the first item in the array. But let's say is at the end of the list, that's like O of n. Do you get? So that's in worst case scenario. For worst case scenario, that's O of n. You need to like traverse through everything, like iterate through everything. So that's O of one. When you don't know the index, that's O of n. But when you know the index, it's O of one. So does that answer your question? Okay, great. So now when you want to remove an item from an array list, you have a question. Someone said they have. Okay, so what's your question? Okay. Okay. So basically when you know the index, right, you definitely want to use an array list for that scenario. Do you get? So and there are other use case of linked list that I would definitely want us to like explore, but time will not permit. We are kind of more out of time. But you don't like in that particular case, you want to use an array, right? That's depending on what language you're working on. So you want to use an array list. Because JavaScript does an array. Remember, I mentioned I kind of clarified the difference between the two. Do you understand that? Does that answer your question? So that's in a web scenario, right? Let's say I don't know why you might want to do that, but let's say you send all your data right to the front end and the client, that's your browser, already have details of all your maybe the values in your database you get. So and you have the index there. Maybe you save them into an array and you want to like retrieve them by the index. You know, in that case you have the index. So it's faster to use the index to like get the value of that particular element. So do you understand that? So I'll definitely like talk about some of the real life scenarios of some of the use case of linked list and array list and the likes moving forward. So now when you want to remove an item from an array list, so you see that it takes longer time to remove an item from an array list. When you want to remove from a linked list, okay. So I will explain why. I think I already mentioned it, but um I will explain why. And I will ask questions. So be ready to answer my question. So now in an array list, when you want to remove an item, remember that what happens is that let's say we have let's say five items from in this array list, for example, and let's say we want to remove, the operation we want to perform now is remove, right? Just take this one out and delete it, you get. So what happens is that is try to like update the index of every other. element in that array. Do you get? So you try like, let's say we have zero, the element one is index zero, one, two, three, like that. So when you want to remove an item, so you try to like update all the indexes of every other element inside the array, and that process is like a long process, creating a new array list, then adding some of those elements into the new one, and just making sure that after it has removed that particular item. So it takes a long time, depending on the size. It takes a longer time depending on the size of that array list. So, but when you want to remove an item from a linked list, it's a bit faster. And this is because when you check the structure of a linked list, yeah, if I want to remove this item, do you know what I'll just do? All I need to do is just now point this previous one, then point, say, this one no longer points to anything, then this one points to this node here. They get so this particular one here point to this node here. All you just need like update whatever this particular one is pointing to the previous. I showed you the details of a node, like that's a previous and a node and the next one. So do you get? So it's a bit kind of faster because that's the only thing you need to do. Take that element out and just change wherever this is pointed to, and change the value of this, the previous value of this. So now that's the reason why it's a bit faster to remove from a linked list than an array list. So can someone just give me an idea? What did I say about this array list? Is it why is this kind of faster? Why is this slower to remove from an array list? Just one person, very fast, can either omit or drop it because I want us to like cover more slides. So can anybody answer that? Anybody? Nobody. Okay, let's go to the next. Okay, the index, not the values. Okay, great. Great. So I don't want to like spend much time on this because we've actually spent more time talking about linked list and array list. So I've shown you the example how you can add items to it. Like some of these topics are kind of um, very wide. So you need to understand them. So yeah, so let's now. So there is a code here. There's a code snippet here that can actually help us test how fast some of these things are. Like what will happen when you have p big records? What will happen? So you see here we have like 100,000 items here, and we want to like kind of add it to both the array list and the linked list. So and I already have some set of code here that can help you track how long it take. So some of you when you are just writing like a very short program that have like maybe um, 10 element or 20 elements, then you run it and it's very fast. You see that there are some systems that are currently that you guys currently use that maybe the developer that wrote it did not consider when the data will be large. And when they just write those codes, you just find out that it works fine. Like when they are testing locally, some of you have experienced that you are testing it locally and it's very fast. But when they give you like 10,000 record and when they give you like 100,000 record like this, then you see that your program starts slowing down. So that's the reason why data structure and algorithm is very important. You need to understand which data structure to use and which one not to use for a particular scenario. So let's just run this. Let me try this. Let's just run this particular code. So I give you an overview already. We're adding elements into this array list and linked list, and also trying to retrieve this element from the array list. Over here, we'll be retrieving from a linked list, and there are already comments stating, there's a particular variable here tracking the time that this particular program started and when it ended. Then it's going to like output results in the terminal for us. So let's just say okay, and I think the other ones also adding a particular testing the speed when you want to add at the beginning of the array list and testing the speed when you need to add at the beginning of the linked list. Some of the things that we actually mentioned. So let's test this and run and let's see how long will it take. So you see what happened when I ran this. My system is already taking some time. It displayed this on this one very fast. That's adding um, took more time, right? So then the entire program is complete. So you see that when you are trying to access a particular variable, let me go down here. I'll try to spend very few minutes on this so that we can cover every other one. So you see this particular string here to time to access elements in our array list. So the same thing here. So when we are trying to like retrieve item from our array list, so we added the same number of elements. We added 100,000 here, right? And now we are trying to like retrieve those data. You see that it's very fast, right? It took like definitely from the number, right? It took like let me say this like 1 million nanoseconds, like 1.8 million nanoseconds. But when you want to retrieve elements from a linked list, it took, I don't even know this number. You should that is very long. I think it's about 11 billion. I think it took 11 billion nanoseconds. So imagine when you want to access, that's because remember that a linked list, right? It needs to like traverse through it, like move from one node to another to get the item. And remember that we are calling the same get method, see. And remember when I say when it comes to Java, they both implement the list interface, right? So you see that it took more time, right? Because there's a way I keep track of the time here and check when it ended here and displayed it. So it took more time. So when you want to add an item in the front of an array list, let's go down here. You see that it's slower than when you want to add an item. And remember that someone already answered, and I gave reasons for that. That's because it needs to like update. You want to add item to the front of the array list. So every other element in that particular array list, their indexes need to be updated, and most likely you might need to like it might create a new array then copy everything that so it will take more time. But when it comes to a linked list, it's faster, right? It's faster to add item to the front of the array. So I just like wrote this particular code to just um show you different. So, and I gave a summary here. So I will be sharing this code, like I said, so you can go through this, and I added a summary of when you're trying to access and the best one, which one is faster and which one is good for a particular scenario. Do you get? So let me see in summary here. When you need fast random access to elements, and when the list is read more often than modified, that means you read from that list more than you modify it. That's use an array list, right? But when you need a linked list is when you need fast insertion. You need to like save something. You need to save something faster. Save something or delete an element. When you want to like insert or delete an element faster, then that's when you need to think about, do I need to go for a linked list? And especially in the middle, like you see what it says, especially in the middle of the list, or you don't need to access element at a specific position frequently. So when you don't need to like you hardly need to like access element from a particular position frequently, and you need fast insertion and deletion. That's when you need to think about, okay, I think a linked list will be perfect for this particular scenario. Do you get? So that's the real life use case. So our time is a bit fast spent, so I'll just talk about some other data. So we talked about. I said we'll be talking about um yeah, I think I'll also talk about the queue before the map data structure. Good. So now let's just start with the queue data structure. So what is a queue data structure? We're talking about linked list. We're talking about array list and on all those data structure that have that kind of list structure. So what about queue and stack? So they are very similar, right? So they are both linear data structures, and they store a collection of elements in a specific order. However, they are different in the way they add item or the way they remove items. So we have queue and we have stack. So now for queue and stack, they are very similar because they are linear, right? But when you want to add an item to a stack, and when you want to add an item to a queue, an element to a queue, the way they work different when you want to remove from them. And a very good example is in a bank, right? You all line up, right? And let's say you are the first person in maybe in the bank, you'll be at the first, right? Then other people will be at your back. That was an example of a queue. Like I think that was kind of pretty straightforward. And and what happened is that when they need to attend or they want to like remove someone from that particular queue, they will pick the person that came in first, right? So it means that if anybody asks you and say, what do you understand by a queue data structure? It's the kind of data structures that when you need to like remove an element from that queue, or when you need to like dequeue, then it follows a first in first out approach. Do you get? So it follows a first in first out. That means the first person or the first item in that particular list or in that particular um, data structure will be the first one to be removed. What do you say? Okay, so that means the first element in that particular key will be the first one to go off. But when it comes to stack, it doesn't work that way. The first element in that particular stack will definitely be the last one out. So because in case of queue, you can add to the bottom, right? You can add to the rear, right? They call it rear. You can add to the rear and remove from the front. But in case of stack, I know some of you that have studied computer science, you'll have maybe heard about stack and queue. In case of stack, you perform this removal or insertion at the same end at the top. So you push or you pop. So meaning that this guy might be the first item in this stack, but it's going to be the last one out. So you see last in, first out. So the last one in with the first one that will be out. So an example is real life scenario is like a queue in the bank, a stack. You can see here when you have a stack of books or a pile of I think clothes. So I don't know what that is. Yeah, so a queue. The same thing in a bank. You can add to a queue or you can remove from a queue. So in Java, let me show you um the code implementation for a key. So it's kind of similar. You see with adding and the only different now when you want to remove, you need to like call in a queue, you need to like call this remove method. So you see here now that we can keep adding to a queue. And remember what I said, you can add to the rear, right? Then remove from the front. So that's for a key. So when you add this item, when you keep on adding item, keep on adding item, but it keeps following that same order, the first one will be the first one out. But in case of even though you added them similar, like if you see that over here now, like I'm pushing, I created a stack here and I'm adding item, I'm pushing into the stack. Alice, I push in Alice, then Bob and Charlie. And when you want to remove from it, okay, let me just show you. Let me just run this code and let's see what happens. Let's see what happens. So you just need to like be aware of some of these data structure and use them. So now see what happens. I need to let me just have a kind of so that it will separate that one. Okay, good. So you see what happens now when when I was trying to like print or display this now in my terminal, you see that it displays Alex was the first one in, right? And Bob is the second one in, Charlie is the second one. Then you see when I was trying to like display it right, then it displays Alice first, then Bob, then Charlie. But in case of a stack and data structure, then I added Alice first, I added Bob next, then I added Charlie last. Then when he was trying to like remove item from the stack, so what happened that Charlie came in first, and Charlie was the last one that was added into this particular um, stack. The next item was Bob. The last one was Alice, and Alice is the last one that came in, and Alice was the first one to enter that particular stack, but is the last one that got printed. So now you need to like just understand the difference between the two. You get so you might be asked what's the major difference between a queue and a stack. So those are just the major difference, and they have like real life scenario, like when let's say you're trying to, that's a bit more advanced, like when you're trying to like trade through, or when you're trying to like find um when you're working like graph, when you're working with graphs majorly, so you like see that you need to like select, okay, which one will I use, will I be using a stack or a queue to like perform some of those operations. That's a bit advanced, and I don't want us to go deep into that. So now let's talk about a map data structure. We have 5 more minutes. Wow. So let's talk about the map data structure. So map data structure in Java basically is just a data structure that stores um, elements in key and value pairs. You get that stores elements in key and value pairs. So it means that like an array list, all you need to do is just add an item, right? So when we're working with an array list here, all we did is just pass in a single item or element here, right? Volvo, BMW, Ford, and the likes. But in case of a map data structure, it doesn't work that way. So what you need to do is when you try to add an item inside a map, for example, you need to pass a key and a value, a key and a value. So my ID is the one adding this one. So normally you will not have to see the key and value, but it's just trying to tell you that Alice is the key here and the value here is 25. And when you want to like iterate through it, you need to, in Java, you need to kind of convert this to a kind of set, then iterate through it, then get the key and the value. So in let's say in JavaScript, so yeah, JavaScript has map, but if you want to like kind of picture what an array list will look like, sorry, a map will look like in JavaScript, then you need to think about like objects. In objects in JavaScript now, you have a value, you have a key, then you have a value. Then when you want to like point to it, and yeah, this map here is like one of the most important one. I wish we can like play around with this, because you can when you add item into a map, when you want to like maybe retrieve it by the key, it is O of one. You can, and this value um, 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 can be of any data structure, do you get, or of any data type. So, and it's very fast. So map is like one of the most important one, like one of the most important one, to be honest. Like whenever I'm trying to solve data structure and algorithm questions, like map is always at the back of my mind, that if I need to do anything, I need to like just fall back to use a map. And okay, if I want to like maybe, okay, let me just, we still have more time. We have 3 more minutes. Okay, so for those that are interested, maybe I don't know, maybe we'll find time to like maybe discuss more on this, but we don't want to exceed our time. We always try to keep on to 1 hour. But majorly, let's say you're working with any kind of data structure and algorithm question, for example, map can be very useful, right? You might need to like just check something, check if a particular value exists. For example, like if you check this particular map now, I can easily check instead of uh, some other data structure that might be a bit crazy. See, there's a contains key. So you can easily use this contains key, for example, and just check if a particular key exists. And that will kind of save you a lot of computation time, or save you some processing time there. So if you have any question, I think that this is where I'm going to stop. And we still have other sections that will kind of talk more about maps and some of these other data structures in depth. But we just want to like expose you to some of the data structure and where they might be very useful. So if you have any question, it's the time to ask question. Thank you very much. Okay, yeah, so you can go ahead.